You'd think making a computer faster would be easy, right? If your program has a million instructions, why not just run all of them at the same time? Well, it turns out it's not that simple. There are these fundamental rules, kind of like traffic laws for data, that get in the way. There's this hidden web of dependencies that really governs how fast we can possibly go. All right, so here's what we're going to cover. First, we'll dive into the rules of parallelism, what's actually holding us back. Then, we'll look at a formal test for when things can run side by side. After that, we'll see the gap between the ideal software world and the real hardware world, explore the balancing act of splitting up tasks, and wrap up with a tour of how processors are physically connected to make all this magic happen. So this is really the heart of the matter. It feels so obvious, just do more stuff at once. But the thing is, program instructions are often tangled up. One part of your code might be busy calculating a number that another part needs just to get started. These are called dependencies, and they're the entire reason we can't just throw a million processors at a problem and expect it to finish in a nanosecond. Okay, so to really get this, we've got to understand the different kinds of dependencies that cause these log jams in our code. Think of them as the fundamental laws of parallel computing. Let's break down the big ones. First up is the one that probably makes the most sense right away: flow dependence. This is just basic cause and effect. If instruction number 2 needs the result from instruction number 1, well, instruction 1 has to finish first, period. There's just no getting around it. It's like baking a cake. You have to mix the batter before you can put it in the oven. And this little bit of code shows it perfectly. Look here, statement S1 loads some value into a little storage spot called register R1. Then, statement S2 needs to add something to that value in R1. S2 is literally just sitting there, waiting for S1 to deliver the goods. That right there is a textbook flow dependence. All right, next up, we've got something a little trickier: anti-dependence. This happens when a later instruction is about to write a new value to a location that an earlier instruction still needs to read the old value from. If you let that later instruction go first, it would just blow away the data before the first one could even see it. Your whole calculation would be toast. Okay, let's go back to our code example. Now check out the relationship between S2 and S3. S2 needs to read the value that's in register R1. But look at S3. It's trying to write a totally new value into that exact same spot. If S3 jumped the gun and ran before S2, it would overwrite the data that S2 was counting on. So the system has to make sure S2 gets to read first, then S3 can write. And that is anti-dependence. And the last of the big 3 is output dependence. This one's basically a fight. You've got 2 different instructions, and they're both trying to write their answer to the very same variable. Whichever one runs last is the one whose value sticks. So to make sure our programs aren't just a chaotic mess, we have to enforce a specific order. And just to be thorough, there are a couple of others to know about. Control dependence is when a chunk of code might not even run at all until some if statement figures out if it's true or false. And then there's resource dependence, which is just a physical problem: 2 instructions trying to use the same special part of the processor at the exact same time. Okay, so we've got all these rules that stop us. But how do we know for sure when we can run things at the same time? Well, way back in 1966, a computer scientist named A.J. Bernstein came up with a really elegant formal test to figure that out. And here they are, Bernstein's conditions. Now, it looks a little bit like abstract math, I know, but it's really just a super precise way of saying what we just talked about. For 2 processes to run in parallel, 3 things have to be true. First, what the second process needs to read can't overlap with what the first one writes. That avoids flow dependence. Second, what the first process reads can't overlap with what the second one writes. That avoids anti-dependence. And third, they can't both write to the same place. No output dependence. If you pass all 3 of those checks, you're golden. So let's put this to work. Here are 5 simple processes. P1 makes C. P2 uses that C to make M. P3 uses B and C to make A. You get the idea. Just by eyeballing it, any guesses on which ones can run together? Well, Bernstein's conditions give us the real answer. And this graph makes it perfectly clear. Every solid arrow is a dependency, a stop sign for parallelism. See the arrow from P1 to P2? That's because P2 needs the variable C that P1 creates. That's our old friend flow dependence. But look over at P5. It's using G and E and making F. It's in its own little world. It has no conflicting inputs or outputs with the other processes, so it's totally independent and can run in parallel with all of them. So here's a fun wrinkle. Just because your program theoretically could run 1,000 things at once doesn't mean your actual computer can. And this brings us to a really crucial idea: the mismatch between what the software wants and what the hardware can actually do. Yeah, this slide says it all. The graph on the left, that's the software's dream world. It shows we could do 4 things in the first step, 2 in the second, 2 in the third, and be done in just 3 cycles. Awesome. But then you look at the graph on the right. This is reality on a processor that can only handle 2 instructions at a time. Those hardware limits create a bottleneck, and the exact same job gets stretched out to 7 cycles. That gap is one of the biggest challenges in computer design. So, to try and close that gap and really squeeze every last drop of performance out of our hardware, we have to be clever about how we slice up our programs. And this means walking a very fine line, a balancing act between how big our tasks are and how much it costs for them to talk to each other. Let's nail down 2 key terms here. First is grain size. That's just how big each chunk of parallel work is. A fine grain could be just 1 or 2 instructions. A coarse grain could be a massive function. Then there's latency. That's the price you pay for communication. Every single time those parallel chunks need to sync up or share data, there's a time penalty. And this diagram shows that whole spectrum. Down at the bottom, at level 1, you have that super fine-grained parallelism, just individual instructions. This gives you the most opportunities for things to run at once. But it also comes with the highest cost, tons of communication and scheduling overhead. As you move up to coarser grains, like whole jobs at level 5, you have way less overhead, but also way fewer chances to run things in parallel. It's a trade-off. So how do you manage that trade-off? With clever tricks like grain packing. And this slide shows it beautifully. On the left, you've got this messy, fine-grain graph with 17 different little tasks and a spiderweb of communication between them. On the right, a smart compiler has packed them into just 5 bigger, coarser tasks. It totally simplifies the problem and slashes the communication cost. And a lot of the time, that actually makes the program run faster overall, even though it looks less parallel. You know, we've been saying processes communicating this whole time, but we haven't really touched on how they physically do it. How do you actually wire together hundreds or even thousands of processors in a supercomputer? Well, that brings us to our last stop, a quick tour of network topologies. These are what we call static networks, where the wires are fixed in place. On the simple end, you've got something like a ring, where every processor is just connected to its 2 neighbors. Super cheap to build, but if a message has to go far, it's got to make a lot of hops. Then on the complex end, you have things like a hypercube, which is way more connected. It gives messages a ton of shortcuts to get where they're going fast. And this table really lays out the trade-offs. Let's just focus on 2 columns here. Node degree basically tells you how many wires are coming out of each processor. Think of that as the cost and complexity. A ring is cheap, degree of 2. A hypercube gets more complex. Then look at network diameter. That's the longest possible trip a message ever has to take. For the ring, it's pretty long. For the hypercube, it's super short. So engineers have to pick, do they want cheap or do they want fast? Now, besides those fixed networks, you also have dynamic networks that use switches. A simple bus system is like a 1-lane road. It's cheap, but only 1 car can go at a time. A crossbar switch, on the other hand, is like having a personal teleportation device for every processor. Anyone can talk to anyone else, instantly, at the same time. It's incredibly fast, but the cost and complexity are just astronomical. So what's the big takeaway here? It's that getting more speed through parallelism isn't some simple hack. It's this deep, fascinating, and really sophisticated dance between the software design and the hardware architecture. It's this constant balancing act between the dependencies in your code, the cost of communication, and the physical limits of the machine. It's a puzzle where the perfect solution is always, always a compromise.